Hello, everyone, and welcome to this book reading session for the book AI and Machine Learning for Coders by Laurence Moroney. So, in the chapter 1, we'll introduce ourselves to TensorFlow. As it says that when it comes to artificial intelligence, machine learning and deep learning are a great place to begin. When getting started, however, it's easy to get overwhelmed by the options and all new terminology. Of course, we know that AI is a really vast field and has too much to explore. So, we might get overwhelmed with the kinds of options that we get and the new terminologies that we face. This book aims to demystify things for programmers, taking you through writing code to implement concepts of machine learning, deep learning, and building models that behave more as a human does, with scenarios like machine learning, computer vision, natural language processing, and more. So, in this book, we'll understand machine learning, we'll go deeper into the concepts of deep learning, and build some models that are more like human made, with scenarios like computer vision, natural language processing, and etc. And simultaneously, we'll write down the code for each and every chapter. Thus, they become a form of synthesized or artificial intelligence. So, when we refer to machine learning, what in the fact is this phenomena? So, what is machine learning? Let's just take a quick read and we'll jump to what is machine learning. So, let's take a quick look at that and consider it from a programmer's perspective before we go any further. So that this chapter will show you how to install the tools of trade from TensorFlow itself to environments where you can code, debug your TensorFlow models. So first we'll understand what is machine learning, get to the basics, and then we'll understand what is TensorFlow, what are the basic tools that we need for TensorFlow, and finally the code for that and what kinds of environments we can use and where we can write the code. So what is machine learning? Before we get into in and outs of machine learning, let's consider how to be how it evolved from traditional programming, and we'll start by examining that what traditional programming is and then consider cases where it is limited. So traditional programming was very limited to certain scenarios and case studies, but we certainly evolved into machine learning because we needed our machine to do much more than just basic programming. Then we'll see how machine learning evolved to handle those cases and as a result has opened new opportunities to implement new scenarios, unlocking many of the concepts of artificial intelligence. Traditional programming involves us writing rules and expressed in programming language that act on data and gives us answers. So traditional programming was you write the rules, you tell the machine the rules, you pass on the data and you get the result based on the rules that you have already provided. But machine learning, I'll give you just a gist of that. Machine learning is a thing where the machine, we give the data, we give the output to the machine, and the machine actually makes out what are the rules behind that output and it makes its own rules. So we don't have to teach the rules, the machine teaches itself. For example, consider a game like Popular Breakout. Code determines the movement of the ball, the score, and various conditions for winning or losing the game. Think about a scenario where the ball bounces off a brick like in figure 1.1. So here is a brick wall, and whenever we hit one of the bricks, colorful bricks by the ball, the brick is removed. So here is a small code that if the ball collides with the brick, if this ball collides with any one of those bricks, then you remove that brick. The function is called, and ball.dx is 1 in 1.1 times ball in .dx, the function is called, and d ball.dy equals -1 into ball.dy. So we understand this a bit later. Here, the motion of the ball can be determined by its dx and dy properties. So dx and dy are the properties of the ball, so we can understand the motion where the ball is actually going. When it hits a brick, the brick is removed and the velocity of ball increases, changes the direction. So when you hit the brick gets removed. Dx and dy are displaying the velocity of the ball increases and the direction changes. So dx and dy, as we mentioned earlier, are the motion of the ball, the property of motion of the ball, and it determines the velocity that it increases and the direction of the ball gets changed. The code acts on data about the game situation. Alternatively, consider financial service scenario. You have data about company's stock, such as its current price, current earnings. You can calculate the valuable ratio called P to E, that is for price divided by the earnings, with a code like in the figure 1-2. So if you work for company that has stocks and you want to know the P by E ratio with code, you will be like code is expressing the rules. So it's calculate PE for stock, then you read the price using read price function. Earnings, you read the earnings by read earnings function, and you finally return price divided by earnings. So that's the answer that you require, right? So here the rules are, you get the price, you get the earnings. This thing is the rule, and we are returning the answer of that rule returned from the code. Your code reads the price, reads the earnings, limited, and returns a value that is the former divided by latter. If I were to try to sum up traditional programming like this into a single diagram, it might look like, so traditional programming might look like that you provide the rules, you provide the data, and you get the answers. As you can see, you have the rules expressed in programming languages. These rules act on data, and the result, you receive the results in answers. So what were the traditional programming limitations? So model from 1-3, that is this one, has been backbone of development since its inception. But it has an inherent limitation. What was the limitation? So namely, that only scenarios that can be implemented are the ones for which you can derive the rules. So as a human being, if we have the rules, then only we can get the answers. So we have the data is in everywhere, right? But if we don't have the rules, we cannot get the answers. That was the major backdrop of traditional programming. What about other scenarios? Usually they are infeasible to develop because the code is too complex. It's just not possible to write code to handle them. So let's consider an activity detection example. A fitness monitor can detect our activity, our recent innovation. We all have our Apple Watch and smartwatches, and we can certainly detect activity. So based on our heart rating from the heart rate monitors, our watches can understand what kind of activity we were doing. So if the heart rate is really high, it might say that you were actually running or maybe jumping. So, or you did some heavyweight activity because your heart rate is too high. Or if your heart rate is normal, the watch might say that you were just walking around or maybe you were sitting. So fitness monitors that can detect our activity are a recent innovation, not just because of the availability of cheap and small hardware, but also because of algorithms to handle detection weren't previously feasible. So recently, because the availability of cheap and small hardware is there and that was not available earlier, these algorithms were also not there that can easily help in detection of these kinds of activities. So after the exploration of machine learning and artificial intelligence, then only we could develop such algorithms that can help us in the detection of activities. So we have a 1.4 figure here. See, so this girl, if her speed is less than 4, the status would be that she is walking. Then now, if the girl is walking and then girl is running. So if the speed of girl is less than 4, then we'll say that the status would be that she's walking, else the status would be that she is probably running. So if you see that if we go by speed, we might say that at a particular value less than 4, the person or the girl is walking, or if the value of speed goes beyond 4, we'll say that she is running. Now extend this activity to say biking. So if we say that the speed is less than 4, the girl is walking. If else if the speed is less than 12, then she might be running, and if nothing else, then she is biking. So in this scenario we can somehow figure out what kind of activity the person is doing. But if we now think of a scenario where she might be golfing, then we might have some problem here. So if we say that she's golfing, then how can we incorporate the code for golfing into this algorithm in figure 1-6? I think it's not really possible to incorporate it, and let's read ahead. Now we are stuck. How do we determine that someone is golfing using this methodology? The person might be might be walking for a bit, then stop, do some activity, walk for a bit more, and then stop. But how can we tell that this is golf? How can we tell that they are playing golf? So, our ability to detect this activity using traditional rules has hit a wall. But maybe there's a better way. So, enters machine learning. From programming to learning, let's look back at the diagram that we used to demonstrate what traditional programming is. Here we have rules that act on data and give us answers. So now what we did earlier was in the algorithm, we were giving the rules that if the speed is this, then she or he is biking or walking or running. And if the speed increases, then they might be doing some kind of other activity. But machine learning, we take a whole different approach. Here, what we do is that we flip this diagram all around. Instead of us coming up with the rules, what we do is we come up with answers, and along with data we give it to the machine, and the machine will figure out the rules itself. Shows what 1-9 we shows that what this would look like. So if we see the next figure, we'll say that we give the answers and the data to the machine, and it will produce the rules itself. So we are trying to imply is this, that now instead of us trying to figure out what the rules are, we get lots of data about our scenario, we label that data, and the computer can figure out what rules are that make one piece of data match a particular label and another piece of data match a different label. So now what we are saying is that nowadays we have all using wearables like our phone, our watches, anything smart that we use are a form of wearables. So now the wearables can get all the information like heart rate, location, speed. So that all information can be stored in form of data, and we can label it. So the answers would be the labels, and data is the all the zeros and ones that we are collecting. So in this figure 1-10, we can see we have the data in form of binary, that is 0, 1, 0, 1, all different kinds of data, and the sequence of zeros and 1 is different for each activity that are labeled below. Like walking, running, biking, golfing, the data is different for each and every one. So now our job as a programmer changes from figuring out the rules to determine the activities to writing the code that matches the data to the labels. If we can do this, then we can expand the scenarios that we can implement with code. So now we are doing is we know the answers, we know the labels, we have the data. All we need to do is write the code that matches the data to the labels. So machine learning is a technique that enables us to do this, but in order to get started, first we need a framework. So that framework is where TensorFlow comes into the picture. In next section, we'll look at what it is and how to install it, and then in the later chapter, in this chapter later, we'll understand and write the first code that learns the pattern between two values. Like in the preceding scenario, it's a simple hello world scenario, but it has same foundational code pattern that's used in extremely complex ones. So we'll just go through once, and the field of artificial intelligence is very large and abstract and comprising and everything to do with making computers think and act the way human beings do. So what we're trying to do is we're trying to make our machines work like humans work and think like humans work. One of the ways a human takes a new behaviors is through learning by example. The discipline of machine learning can thus be thought of as an on-ramp to the development of artificial intelligence. Through it, a machine can learn to see like a human in field called computer vision, read text like a human, natural language processing, and much more. So let's jump to what is TensorFlow. TensorFlow is an open source platform for creating and using machine learning models. It implements many of the common algorithms and patterns needed for machine learning, saving you from needing to learn all the underlying maths and logic and enabling you to just focus on your scenario. It's aimed at everyone from hobbyists to professional developers to researchers, pushing the boundaries of artificial intelligence. So, what we are here to do is that we are here to implement common algorithms and patterns without the need of knowing the maths beneath it. So, we are not here to do any sort of maths, we're just here to implement common algorithms and patterns to get an answers, right? So it also supports develop deployment of models on web, cloud, embedded systems, etc. Now let's understand the high level architecture of TensorFlow. In TensorFlow, you get to you get to train, deploy, save, and analyze your model. Along with that, you have few other things that can help you with the training as well as finding the data, training the models, knowing how to train model, distribute a strategy of training models on different devices, all under the high level architecture. So we learn about them one by one. First, the process of creating a machine learning model is called training. For example, if you want a computer to recognize cats and dogs, you can use a lot of pictures of both and create a model. And the computer will use the model to try to figure out what makes a cat and what makes a dog a dog. Once the model is trained, the process of having it to recognize or categorize future inputs is called inference. For example, you've trained the model for distinguish between a cat and a dog. But if you take another picture, a new picture of a cat or dog that was not in the data you already provided to the model, then if the model comes out with the output that certain picture is of a cat, and that output is what we called as an inference, because the model is already trained and now the model is inferencing that the input image that you provided recently is of a cat or a dog. So for training models, there are several things that we need in order to support a model, in order to train our model. So first set of things is API for designing the model themselves. So with the TensorFlow, we have three main ways of doing it. First, we can code the whole logic for how a computer to learn ourselves in the form of code. That is totally not recommended. It's a very lengthy process. Then you can use built-in estimators, which are already implemented neural networks that you can customize. Then finally, we can use Keras, a high-level API that allows you to encapsulate common machine learning paradigms in code. So in this book, we'll be taking care of creating models with APIs, that is using Keras. Now, there are many ways to train a model. So, if you are working on a laptop or a computer, probably you have a CPU, right? So, if you want to train a small model, like you are a beginner and you're learning, and you want to train a small model, then a CPU is sufficient. Sometimes our laptops and our desktops do have graphic cards, so graphic processing units, we also do have them. And there's something new called the tensor processing units or TPUs, which are usually used for like processing very heavy models or training very heavy models, and usually are not required for the beginner levels. In more advanced working and research environments, we usually go for parallel training of our model. So there are multiple chips that can be used, and employing a distribution strategy. So not all data goes into a single CPU or a single GPU. We have a parallel length of them and the data gets distributed, but the trained model comes out as a one from all these distribution systems. The lifeblood of any model is its data. As discussed earlier, if you want to create a model that can recognize cats and dogs, it needs to be trained on a lots of examples of cats and dogs. That's common. But how can you manage these examples? You'll see over time that this can often involve a lot of more coding than creation of the model themselves. So TensorFlow ships with APIs to try to ease this process called TensorFlow data services. For learning, they include lots of pre-processed datasets that you can use with a single line of code. So dataset TensorFlow comes to your help that they have a TensorFlow data services where you get all that data set pre-processed. So you don't have to collect the images specifically. You don't need to worry about the licensing. You don't need to worry about some garbage images coming in, some raw images coming in. The images are already pre-processed so that you can directly feed those images in form of data sets to your models. They also give you the tools for processing raw data to make it easier to use. So if you are saying that, okay, I have my customized data and I want to work on my data myself, so you can also use and pre-process your raw data and make it easier to use. Beyond creating models, you'll also need to be able to get them into people's hands where they can be used. So for this, you can use TensorFlow includes APIs for serving, like say you have trained a model and it is for a website. So you can host your model on a website by using APIs for serving in HTTP connection for cloud or web users, or you want to deploy your models on your smartphone, say Android or iOS, or even some embedded systems like Arduino, Raspberry Pi. So TensorFlow provides TensorFlow Lite that makes the model inference much easier on those such devices. So it's also well used for Linux based embedded systems, that is Raspberry Pi, we have talked before. A fork of TensorFlow Lite called TensorFlow Lite Micro also provides inference of microcontrollers through an emerging concept known as TinyML. So if you want to work on TinyML, so that is related to deploying TensorFlow models on microcontrollers, you can also do that. And finally, for web browsers, we have Node or Node.js, we have TensorFlow.js, so you can easily train and execute your models in the web browser itself, and you don't really need some software on the laptops. Next is how you can use TensorFlow and deploy it and install it on your machines. So using TensorFlow in the section, there are three main ways to install and use TensorFlow. So you can use command line, then you can use PyCharm, and finally TensorFlow also is accessible on Google Colab. My personal favorite is Google Collab because it's really easy to use. You don't really need to download anything on your laptop, on your desktop, and it's all in cloud and your work stays safe. You can easily connect it to GitHub and host it, your projects and your code in GitHub, and you can easily just import and you can easily import new directories, new tools. It's really easy to use. So for Python, the TensorFlow supports creation of models using multiple languages, including Python, Swift, Java, and more. So Python is second as a primary language to work with in for TensorFlow, but you can usually easily use TensorFlow with Swift, Java, and many more. In this book, they're primarily focusing on Python. So first you need to download Python. So you get Python from learnpython.org to learn Python language, and you can easily download it. You can easily support it by TensorFlow team is pip. You can use pip install Python. With Python there are many ways to install frameworks, but default one supported by TensorFlow team is pip. So yeah, Python environment is there, then you can easily install TensorFlow using pip. So pip install TensorFlow, and you should note that starting with version 2.1, this will install the GPU version of TensorFlow by default. So prior it was using CPU version, now you can easily use GPU version. So it gets installed automatically. You don't have to work for it. And if you don't require GPU or drivers, you can still use the CPU version of TensorFlow. So maybe you can say pip install TensorFlow -CPU. So once you're up and running, you can test your version. So you can say import TensorFlow as TF. So it's really easy. So if you call TensorFlow as TF, because every time writing TensorFlow kind of is difficult. So you can easily print TensorFlow dot double dash double underscore version double underscore. You can see output like figure 1-12. So it says 2.2.0.0, that is TensorFlow 2.0. So now I'll be skipping through the process of installing PyCharm and how you can use it, but I'll just brief you all about this. That PyCharm can be easily used when you want different versions of TensorFlow for your different projects. So it really helps you there, that if you want to use TensorFlow 2.0 for one project and 2.1 version for another, you can easily separate the two virtual environments. Then here's an image of how you can create a new virtual environment using PyCharm. You can set up new environment, you can choose the Python version and just click on create. Finally, you can see all the packages. You can add these packages on the virtual environment when whatever you want to use, and TensorFlow is also available in one of these packages. Finally, if you want to use Google Colab, you just need to log in to your Gmail account, go to Google Colabs, and first thing you'll get is your previous projects if you have any, or you can just click on start a new notebook. You can get your code from GitHub or upload one from the Google Drive, anything you like to start your new code with. And also Colabs do provide you with support of GPU and TPUs for your state-of-the-art models. And here is running TensorFlow code on Collab. So in Collab, you can use pip install TensorFlow double equals 2.1.0. Any installation of tools that you need, you can easily install these built-in TensorFlow libraries. And yeah, so as you know, you can use any of these things to run your Python code and download TensorFlow, install TensorFlow, and work with it. So getting started with machine learning, we'll be starting in the next video. And meanwhile, I hope this video was really helpful to you, and see you next time. Thank you.